Great. Okay, good evening, everyone. Good evening to those online and to those in person. Great to see you all, and thanks for coming along to our new venue as well. So it's nice and cozy in here. I hope you're all comfortable at home. So tonight we've got a lovely talk ahead of us. Firstly, this is just the usual spiel of as a Royal Meteorological Society event. Thoroughly encourage everyone to join if you haven't already. There's plenty of benefits in doing so. We're going to run this as a hybrid meeting, as you all know. We'll try and interact with the audience both in person and online for the question and answer session afterwards. So I'll try my best to chair that. And the talk will be recorded and placed on YouTube afterwards and by permission. Okay, so on to the talk. We give a big welcome and grateful to our speaker tonight, who's Hannah Bloomfield from Newcastle University. Hannah is a Newcastle University Academic Track Fellow in Climate Resilience Energy Systems. She gained her PhD from the University of Reading in 2017 and has since worked on climate services projects with relevance to the energy and finance sectors. Hannah specializes in modeling UK and European electricity demand and renewable generation. She's also worked on developing these tools for Mexico, India, and multiple regions of Africa. A key outcome of her work has been to improve the accessibility of large data sets to energy system modelers and policymakers, and to understand key weather conditions which lead to energy system stress. So the talk tonight is titled, How Can the UK Move Towards Climate Resilience Net Zero Energy Systems? And so tonight, Hannah's going to talk to us that energy systems are becoming increasingly exposed to the impacts of weather and climate due to the uptake of renewable generation, increasing the need for high quality meteorological data within energy system modeling. So Hannah's going to discuss ways that present and future power systems will be impacted by weather and climate variability, and we'll consider examples of which weather conditions provide the most challenging periods of UK energy system security, such as prolonged low wind and low solar power generation. If these occur during high periods of electricity demand, then system operators can face significant challenges. So the impacts of climate change on both energy and demand and generation will also be discussed. So plenty to get through. We're looking forward to it. And as I say, there'll be the question and answer session afterwards. Yourself, Hannah.
Great, thank you. Yeah, hi everyone. Thank you firstly for giving up your Friday evening. It's lovely to be here. Thank you for inviting me. So yeah, as Greg said, that's what we're going to talk about today. Some thanks to some people on the screen there. Combination of PhD supervisors, previous bosses, friends, and lots of people I've worked with to do this work that we've all been involved in. If at any point you get too hot or cold, like I know we're playing like heating juggle, please just like wave at me and we can press the buttons. Like that's fine. So the big challenge, which I'm thinking about a lot at the moment, is rapid decarbonisation. So this is a global problem, but today we're predominantly going to talk about the UK. So we've got to reduce our fossil fuel consumption. You know, it's wonderful to talk to a meteorological society because I don't have to say some of you might think climate change is happening. I think we're all on the same page there. Climate change is happening, less fossil fuels, and we need some solutions, right, to operate our energy systems in a more sustainable way. So one of the big options is building renewable generation, so wind power, solar power and hydropower, all dependent on weather. But inherently, these are very variable. And to cope with that variability, we might also need to build some new technologies like energy storage, maybe having hydrogen networks where we can run networks on hydrogen fuels rather than gas. We need to invest hugely in our energy infrastructure as well if we're going to build all these new wind turbines and solar panels. So we have this kind of energy side of the problem. And we also have what we're probably all more familiar with, the climate side of the problem. So as I said, all these components are weather dependent. Extreme weather events, it is very cold at the moment. That means we've got this increased kind of demand. We've recently had a lot of named storms. Henk and his friends cause issues for energy system disruption. But then there's some more broad things like the impacts of climate variability and climate change that we'll talk about today. So the big key things as to why I'm employed at the moment is to kind of think about how we can maintain a sustainable energy supply. What do we need to invest in? And what might cause us these big resilience challenges? So resilience is kind of a really big buzzword in the way that academics are funded at the moment in a lot of sectors. But it's really about how do we keep the lights on when we've got all these different challenges that we've maybe never experienced before with our historically coal and gas-fired systems. And the real thing when we use loads more wind and solar power is meteorologists become really important when you're thinking about energy system modeling. So historically, not that many weather forecasters were involved in power system modeling, like oil and gas and coal. You can just turn it on and off when you want it. If it's colder, not a problem, right? We can literally just turn things on and off. When you've got wind farms, you need really high quality weather forecasts to come with that because we need to know when there might be periods of really high or low wind, and then there's uncertainty associated with that we need to deal with. So that's the kind of challenge. So if we step back a tiny bit, why do the energy sector care about weather? So what are the most weather dependent components? So the number one bit is energy demand. So the red box there, our demand is dependent predominantly on the temperature. So the colder it is, the more we put the heating on. This room is an excellent example of some high energy electrical heating on the wall. They're probably spending quite a lot of money on that for us. So getting our money's worth. Wind chill as well. In the meeting today, we're talking a lot about cold easterly winds coming into Edinburgh and how that might, really impact the demand for your energy. Also in the summer, relative humidity. If it's hot and if it's sticky, it tends to feel a bit hotter. And maybe we're moving into a world where people start to have air conditioning, particularly in southern England, but in other countries around the world, that's already a huge thing, right? So then we've got renewable generation. So wind speed for wind power is the important variable. The solar generation is about how many hours of sunshine you get a day, your shortwave irradiance, but also your temperature. So solar panels aren't as efficient when you're at very high temperatures. So when you're in a heat wave, even though it might be really sunny, you get this reduced efficiency of your panels. And hydropower, depending on your amount of precipitation you get, river runoff, and in countries like Scandinavia and in small parts of Scotland, very dependent on snow melt. So you need a really good snow season to then melt in the spring and fill up your hydro reservoirs. And the final picture on here is bits of the network. So extreme weather can damage energy system network components. Big storms, heat waves, floods, all cause problems. So we care about the weather, and multiple timescales are important. So I mentioned weather forecasts earlier for demand and wind power. That's really important for your hour to hour, just keeping the lights on. But I also mentioned that, we're moving into a world which needs to have a very different energy system, and that will have an underlyingly different climate. So the climate will be warmer and wetter when it's changed. That will mean that potentially our patterns of demand that we use might just be quite different. Also, potentially, due to climate change, we'll have different wind patterns, a different amount of cloudiness each day. So lots of timescales are important. Between these, we get this kind of range of like seasonal forecasts where all the big energy traders in London make their money, hedging how much gas demand we might get in the coming season. Probably some people made a lot of money on seasonal forecasts for the period we're in at the moment. And with policymakers as well, this kind of idea of energy systems is and how they might transition to net zero is a really hot topic. So this is a report that came out from the Committee for Climate Change in March last year. And there's just a few quotes for it on the screen there. So they put on in this report, this was a big energy system modeling consultancy exercise, a reliable, resilient, decarbonized electricity system. It can be delivered by 2035. The first question is, can we do it, right? Can we get to net zero? And the science says, yes, no problem. We just need appropriate investment. We'll leave that hanging there for the government. But the report highlights a lot of challenges. So by the time we're in this net zero energy system, We'll get more frequent and more intense weather events such as heat waves, droughts, and floods. They must be anticipated. And a really interesting thing that comes out of the report is other likely changes to weather. The possible changes in wind conditions are increasingly critical to the function of the whole energy system. And we'll talk about that a lot more later. So just to think about some of the things that are impacting us right now, this is just, there are hundreds of newspaper headlines, but these are just three I picked out yesterday. Storm Eunice, which happened, was it last year, 2 years ago? I'm sure time passes. 10,000 homes in the southeast left without power. Some homes without fresh water supplies for up to a week. So this is a very interesting problem that if you, our water treatment plants need good energy supply. If we haven't got power, you can't have clean water, which arguably is much more useful than electricity for us. Storm Arwen. Arwen was a big event which impacted Scotland and lots of Northern England. So this was a real important event in terms of the government realizing this idea of cascading risk crises and the fact that when you have one of these big winter storms, it can take out bits of power network, and then we can have knock-on problems from this. We can see quotes here. You know, they had some real contingency planning had to happen after this because it was really quite serious. And then Storm Henk, the main thing we saw in the news about this was the flooding, like catastrophic flooding, but also lots of power outages, both associated with the wind and the flooding that came. So lots of extreme events, all impacting our energy system. So the first question I often get asked as a climate and a meteorologist who talks to energy system modelers is like, well, why can't we just use our data? You know, the energy system reports how much wind power is generated every hour, how much demand there is, and this is all publicly available data. But the problem we have here is we're in a period where the energy system is changing so rapidly, like the climate, that this data actually has a lot of trends in it. So this is a graph that's showing Great Britain's electrical supply in terawatt hours per year. And the important things here is the black section is how much coal we're using. So you can see as you go through from 2009 through to now, our use of coal is drastically decreased, which is fantastic. And the green section is the amount of wind. So the wind is growing, and we build turbines, well, all over the place now, actually, but the turbines are not always built in the same location. So there's large trends in this metered data. So if you're interested in resilience challenge to today's power system, historical data that the energy systems modelers have is not really relevant because the system is changing so rapidly. So what we have to do is we have to build them meteorological reconstructions of present day systems, and we put past weather through it. So that's a bit of what I'm going to talk to you about today. The first thing I'll talk to you about is some energy meteorology data sets that I made during my time at the University of Reading, and we still use now. We'll then use them to think about the impacts of climate variability on power systems. We'll think about some kind of new special emerging extreme events that as a meteorologist, you really just might never have thought about before. And then we'll think about the impacts of climate change. So how do you go from weather to energy if you want to create some of these kind of time series maybe of electricity demand, wind or solar? So what I do is I use gridded weather and climate data, products called reanalyses. So historical reconstructions of past weather. Lots of these are available, all gridded, often global in their spatial scale. So as you mentioned, I also do these kind of projects for Mexico, for India, and for parts of Africa. But the premise here is we can take meteorological data. We know how it relates to energy system operation. You know, we know we have these weather dependent parts of it. And we can fix our power system setup. So the example here is we're saying, you know, we'll say it's 2021. We know how the system operates in 2021. We know where our existing wind farms are. We know how many solar farms we've got. Let's imagine we had, say, 50 years of weather all running through today's system. And then we can think about how different meteorological conditions might impact our present day system. So you can start to ask questions like, well, what would happen if the winter of 1962-3 happened now? You know, what would happen to the energy system? Would it fall over? So my models, the outline of them was on here. We go from temperature to demand, we go from wind speed to wind power, and we go from temperature and shortwave radiation to solar power. So the demand is a linear regression model. So this is just a statistical function. Don't worry, as it's Friday. I think there's only 3 equations in the whole presentation. So bear with me. So demand is a function of LTT is a long-term trend. So we have lots of stuff that is nothing to do with weather that cycles over years that affects our use of energy demand. So things like COVID, things like appliances getting more efficient, things like our behavior changing over time. GDP impacts this quite a lot. So we have a long-term trend. Which day of the week it is massively impacts our energy demand. It's much higher Monday to Friday than it is on at the weekend. Also things like Christmas, when everyone's on holiday and heavy industry isn't running, we use a lot less energy demand. So we count that as kind of a special weekend. And then we have these weather terms. So we call them heating degree days and cooling degree days. So what you can do is you can take the temperature, we can aggregate it over the whole of the UK. So take an average, and then if that average is less than 15 degrees, that's when people tend to put their heating on. So these numbers kind of come from statistical analysis of how people act. Because you might think, oh, 15. Speak to Scottish people and they're like, oh, I wouldn't put my heating on if it's 15 outside. That's absolutely fine. In London, you're like, it's already on. So yeah, on average, that's how people respond. So higher heating then. And in summer, if it's over 22 degrees, people who have air conditioning tend to put it on. So these kind of models fit very well. You can see an example here for France. So this is temperature versus demand. France has a lot of electrical heating. It's got a really good fit. And you start to see this impact of air conditioning ticking up there. So we could do this. And the other nice thing we could do with these kind of models is that the weather doesn't care what day of the week it is. So we can set the parameters. So if you care about Sundays and you care about, well, maybe we've got too much renewables, you can set every day as a Sunday in the model. And you can think about really low demand events with different weather. Or if you're like, what is the biggest challenge? Our highest demand day is a Wednesday. You could set every day as a Wednesday, and you could put all the really cold temperatures through the model, and you can start to really create some difficult weather. So we have demand. The next big one is how we do wind power generation. So this is a physical model, and the relationship between wind speed and wind power is quite complicated. So let's just look at this for a minute. So wind turbines are all characterized by something called a power curve. So that's the relationship between hub height wind speeds. So we'll say around 100 meters is the top of a big offshore wind turbine. And capacity factor. So this is the percentage of power you're getting out of the turbine compared to if it was running at absolutely optimal conditions. So it never quite hits 1, or, 0 to 1 rather than percent. So it never quite hits 1 because they're never, if you've got across a whole farm, there's always some turbulence. So there's always something preventing it being truly perfect, but you get pretty close. So at very low wind speed, you get very little power. Then you have this kind of cubic region. So small changes in wind speed can lead to quite large changes in wind power production. There's then quite a flat bit on the top, and then it drops off after 25 meters per second. So after 25 meters per second, the wind farms shut down to protect themselves. So these are like big storm conditions. It's a lot of money to send a man out on a boat to fix a wind turbine. So you want to get them to look after themselves as much as you can. Newer turbines maybe are getting a bit more resilient than this. The bigger they get, the more you can stretch these curves and make the productive region as big as possible. But, this is a rule of thumb. So you can kind of see the weather forecasting challenge here, right? That if you get a very small error in your wind speed forecast, that can lead to a very big difference in your wind power forecast. So that's difficult. But the way we kind of model this, so we take our reanalysis wind speeds, we throw them through the power curve everywhere. So we get this full kind of gridded representation of wind farms, but we know where the wind farms actually are, so that we've got our offshore wind and our onshore wind on those little pictures on the right there. So the darker the color, the more wind we've got installed. We can then aggregate this and weight by where we know the turbines are. And then we've got a national time series of wind power generation. The other thing you could do is leave it at the farm level if you were really interested in individual wind farm forecasting. So we do this, aggregate to national level, and the final model is a solar model. So this is the kind of empirical relationship between solar power generation from a panel is pretty simple. It's just these equations. In the real world, they don't run quite this perfectly. But for a modeling approximation, we'll take this. So you have your incoming irradiance on the panel. We kind of assume in our grid box of weather data we've got a kind of uniform distribution of panels. It's a ratio of standard test conditions. So when the panel is designed, there are these kind of optimal conditions that they test it in to make it as productive as possible. So it's a ratio of how much radiation you've got compared to that. And then there's this efficiency term, and that is the relationship between the warmer the cell is, the less productive it's going to be, because there's more resistance in the cell components, so it's struggling to work. And there's this kind of relationship here between irradiance on the panel and capacity factor. So it's quite linear, and the different colors just show you what happens as it gets hotter. So it's not a huge effect, this reduction in efficiency, but it's enough to model it, particularly in summer when it gets really warm. So we have lots of these data sets, and we tend to run them over long periods. So there's one that we've done on a reanalysis where we've got all this data from 1950 through to 2020. We've also done this exercise for forecasts. We've done it for future climate projections. You can kind of do this for any kind of climate model data. And then you can start to play with it. So I'm going to show you now some of the games you can play with this data. So the first thing I'm going to show is not my work actually, but when I joined the University of Reading with James to do my PhD in 2013. In 2013, there was some work going on in the department because National Grid had contacted the University of Reading and said, "Oh, we've been having a bit of bother with these wind turbines," and it's kind of okay, excellent, sounds interesting, scientists like bother, and they basically said, "We've got these data points, and 2010 was an incredibly low wind year," and they were basically saying, "We've been investing all this money as a country building wind farms, and it wasn't windy. What's that all about? Is that going to happen every single year?" And we were like, "Oh, that's an interesting question. We can kind of go and look at that for you." So at the point they came to the University of Reading, it was Dirk Cannon who did this piece of work. We had these points. So this is the Department for UK Energy Statistics, and National Grid had some data. So what they had is their estimate of average capacity factor for all the farms across the UK. And this is where the farms were at the time that we had. So this is from 2012 when they did this bit of work. So these estimates, and you can see that 2010 is much lower as a number. So what we could do is use those models that I've just talked about. There's a very similar version of the wind power model existing at the time, and you can throw past years of weather data through it, and you get something like this. And then 2010 starts to look really interesting, right? Because you can see there that it really was a very low wind year. And there are meteorological reasons for this. It was hugely negative in the North Atlantic Oscillation. It was, some of you might remember those satellite pictures where the whole UK is just covered in snow. And it was quite remarkable what you actually got to see. There's also here, because we're doing calendar years here with the way we've set this up. So if you think we've got January, February, and December, that's not actually the same winter in the way I've presented this, right? So we've got an extreme December with an extreme January, February, which makes this look even worse, even though it's two parts of two different winters. But from this, what you can say to people like National Grid is, well, no, it's not going to be that. The wind power is not going to be that low every year. This is climate variability. You need to be prepared that it could happen again, but you can start to give a bit of a return period. The other thing that's really interesting here is this is 1985 versus 86. So that's a huge year-to-year swing in the capacity factors. Again, that's climate variability. That's something we need to be able to deal with as a power system. At the moment, we've got 22 gigawatts of wind power on the system. The plan is by 2030, we'll have 80 gigawatts. So that's like plus swings like that in 2030 turn into plus or minus 10 gas plants, right? That's what we've got to somehow find or lose each year. So it's quite a challenge. I'm not saying this is easy for our current government to solve, but we can use meteorological data to put this into context. So since then, things got even more interesting. And we got contacted by a lot of people in 2021. So we thought 2010 was bad. Then in 2021, this was actually the lowest wind summer that had happened in the last 70 years. So a nice thing that happened actually is this era 5 data set got a lot longer between that period with the first study. It got extended all the way back to 1950. Now goes back to 1940, I think. Yeah, this is a really low wind year, and we built even more wind turbines by this time. So this really kind of highlights these challenges. We kind of got away with this one because the low wind period happened over summer, and wind speed has a very strong seasonal cycle. So generally, we have much lower wind speeds in the summer than we do in the winter. So the wind speeds being really low in summer, it was a time when our demand is lower. We're not expecting so much generation, but there's no reason we couldn't have a winter like this. And then it's really interesting to think where the power comes from. So this is just thinking about kind of broad, average seasonal conditions. The other thing you can do is think about extreme events for power systems. So normally when people think about extreme events, they think about like heat waves, floods, storms. For power systems, things are a little bit different. So the most challenging weather conditions for a power system is when it's really, really cold. And for us at the moment, really, really low wind, because that means we have to find gas from somewhere. And particularly at the moment, gas is very expensive. So we can use our really long time series of data to look back and to think about, okay, I've got my demand, I can subtract my wind and solar, and I can find the days historically when that was highest. And then that, as a forecaster, you can then use those kind of composites like I'm making here to be like, okay, if I see these pictures in a forecast, we're potentially going to have a very challenging day. So what the weather actually looks like during these days, it happens under very high pressure. So high pressure centered over the UK is the easiest way for it to be cold and low wind. What's interesting here is what's on the plot is if we look through, I think it's 80 years of data and pick the top 50 days, so the 50 coldest, lowest renewable days, they all look very similar. The stippling there, all the dots are if 49 out of 50 plots all agree that was a really cold or really low wind event. So over the UK, this is quite profound, cold temperatures, low wind. What's also interesting is if you look at, because we don't have to just model the UK, we can model the whole of Europe. You can then be like, well, what's going on in the rest of Europe while this is going on? So if you only consider the GB system, the impacts are centered there. Given we get a lot of our power from France, the most challenging weather conditions for the French system are when it's very cold over France, Germany, and the Netherlands. But it's very interesting to see that we have very low wind at that time as well. And what they would be hoping, to be honest, is that we could provide them some wind power at times when they have high demand. But sadly, weather hasn't, the way these high pressure systems sit, they're very large. So the North Sea area of all the wind farms in is still not generating anything when the French system's very hard. So this is for present day power systems. The other thing we're all trying to do is build a lot more heat pumps, right? We're trying to electrify our heating to get away from using gas. And the effect this has, if I just switch between those two pictures, this is really modeling France because they already have quite a lot of electric heating. You can really see that plot gets a lot more blue. So basically, the more heat pumps you put in, the more important the temperature component of these composites becomes. So we become, at the moment, our most extreme days are driven by when it's low wind. And you hear people talk about things called wind droughts a lot these days. But in a future, when we've got lots of wind and lots of heat pumps, you know, that trade-off between temperature and wind speed becomes very important. Just going to skip that one. Yeah, just a point that I find very interesting. So we're talking about this from a very meteorological perspective. I showed you that report at the start from the Committee on Climate Change, which was talking about running a power system model. So there's a lot of things I'm not talking about when I'm showing you these pictures. I'm not talking about transmission. I'm not talking about flow across borders through interconnectors. I haven't considered any energy storage. If you do start to consider all of those components as well as the weather, you get a slightly different story. So this is a bit of a study we did where we compared just the modeling I've shown you there, just what are the most difficult days purely based on the weather, to what are the most difficult days if you do the full shebang and you run it through a really complicated power system model. And it's very interesting that in some years, so the colors here are just showing you how much the system costs to run through different winter periods from October to March. And you could kind of think, well, I think it's difficult in the sense of the higher the cost is, the more difficult that was from a system operation perspective. We've got some blue lines in there, like this is a good example actually. So the most difficult weather day in that period was very close to the time when the system costs were highest, but they're not perfectly aligned. And what happens in scenarios like this is, because we've got options, we've got storage, we've got interconnectors, you might be able to cope on the most difficult weather day, but maybe it's the days after that that start to become very difficult from a full system perspective. So this becomes really fun when you start to work with power system modelers and engineers, just trying to work out, well, how does the weather fit into the wider picture of keeping the lights on? Yeah, so I mentioned earlier the seasonal perspective, thinking about when 2010 had that really low wind year. I mentioned the North Atlantic Oscillation. There's a lot of work in the energy meteorology community that thinks about, well, how much of our demand and renewable variability can just be explained by the jet stream and just oscillations of that through the North Atlantic Oscillation. And to be honest, quite a bit of it can be. So what we're looking at here is a plot on the left of our winter mean North Atlantic Oscillation Index versus our wind power generation. And there's a reasonably good positive correlation there, right? In the winters where the NAO is more positive, means the storm track is more directed over us, which means we're getting more wind, so higher wind power output. But when you start to look at, through these power system models, you start to look at power system costs. That then starts not to be driven so much by just these large scale weather conditions. So we do see that when the NAO is more negative, so when we've got more of those high pressure centers, less good wind conditions, it is generally higher cost to run the system. But you get these interesting anomalies like 1996 to 97 here, where it's actually over the full winter, it was quite mild, quite stormy. Not remarkable. Probably most of us wouldn't remember much about that winter meteorologically, but it had really, really high power system costs, the highest of all the years. And that was because it had this really specialist set of conditions. So we set these power system models up to assume you can do things like store energy. We run them for 2030 systems where we say, oh, we've probably got that technology. The day when the extremes happened meteorologically here happened to align with a period where all the storage was empty. We'd already had to use it for everything else. So a relatively unremarkable weather year was actually one of the most challenging, just by the order that the weather events happened to happen in, that we hadn't had time to charge up the stores. So this is quite interesting from a meteorologist perspective, because when I have to talk to people like National Grid and they're like, what should I be worried about? It's like, well, I want to tell you the most extreme weather, but also sometimes this slightly less extreme weather can be really challenging as well. So let's talk about climate change as a past bit. I think that's a thing that a lot of us are thinking a lot about. What time do I need to stop talking? Just checking I don't go on for too long.
then try and give 50 minutes of Q&A, so sometime.
Awesome, great. We're on time. In case anyone was panicked that I've still got like 50 slides left, I don't. So yeah, impacts of climate change. I think this is really relevant when you think about energy systems, because so much we're thinking about energy systems of the future, and the climate is going to be really different at that point. So there's this really interesting kind of development of climate services, which has happened a lot through universities and through startups and companies, where there's actually quite a lot of online data sets now and pointy, clicky kind of tools you can use to look at climate change information. So this is an output of a project which I was involved in towards the tail end of. This is the ECEM project. So this is the European Climate Energy Mixes dataset. So the whole project was making outputs like the energy data sets I talked to you about earlier, slightly different methods, but doing it for countries across Europe, as you can see, and for regional climate models. So European domain models from the Euro Codex set. So they picked 7 very different climate models. So a lot of science was done to make sure that the models all had a really good representation of the present climate. Present climate, but they had really diverse kind of climate change projections, because for a lot of variables, we're just quite uncertain, right, about what's going to happen. And this tool was designed to engage with energy system modelers so they could start to point and click and explore the data. But we thought, well, we should probably do some science with it as well, right? So we started to have a look at what you could say about different countries of Europe's climate change response. So we kind of had 2 time periods of interest in this. We had 1980 to 2000 as our history, and we had 2045 to 2065. So centered around 2050, as in a lot of policy reports, 2050 is like a point we're aiming at, decarbonizing by net zero by 2050. So it's really interesting, I think, when you look across different weather variables, just to think how different the climate change response is. So there's in each of these plots I'm going to show you, there's bars. So the bars represent different seasons and annual change. So change between this future period and historical. So within each bar, the bar is the mean response over all of the climate models, and each dot is an individual model response. So this is from those Cordex models. So yeah, mean climate model response, and then we've got this kind of uncertainty bar around it. So you can see this is a 20-year period. If you've got a very small bar around that, it basically means if you do the uncertainty analysis, a lot of the years look very similar. There's not much impact of individual years. If the bar looks large, it means that the impact of climate variability on this result is quite big, and we're quite sample sensitive in this 20-year period. So if you just look at, rather than energy, if you just look at weather variables to start with, we average over the whole of the European land. We can see that with these different RCP, so different future climate projections, both of these are quite high end, 4.5 and 8.5. You can see that the higher the projection, the warmer Europe is getting. So the climate models are doing the right thing. No surprises there. And there's reasonably uniform responses across the seasons. You see, if you look at wind speed, the models are very uncertain. Some of these models think wind speeds will increase in the future. Some think it will decrease. The multi-model mean is not very representative of what an individual model is doing. And honestly, it's just quite confusing. To explain to a non-expert how you interpret this is quite hard, because some of the people we talk to on these projects are engineers who don't know anything about weather, and they're just like, what's my wind farm going to do? And it's like, well, I don't know. And I'm not sure anyone does. So we can do this for weather variables, for energy variables as well. So let's start with demand across Europe. So the impact of climate change on demand. When you look across the whole of Europe, overall, our demand is going to go down by 2050 if we kept today's present power system, right? You can argue that maybe demand might increase a lot as we change behavior. But if climate change was the only factor, demand would actually go down a lot, because we're getting less cold weather by 2050. But you can see there in summer, we've got quite a big increase. So this is around the uptake of air conditioning and people actually really needing that by 2050, particularly in Southern Europe, where potentially they're using air conditioning outside of the summer season. So the impact of year-to-year climate variability here is largest in the winter. In the summer, it's pretty small. But this is quite a nice bar chart, I think. The response is quite clear. If you break it down between individual countries across Europe, you start to get quite different responses. So you see in Sweden, never gets warm enough in Sweden in these model simulations to use air conditioning. Demand is just going down in all the countries, sorry, in all the seasons. Whereas in Italy, you can see that really huge demand in summer goes up by 8 or 9% because it's just getting so warm. Everyone is starting to use air conditioning. So yeah, this is interesting, quite well defined. Again, when we go to look at wind power, things start to get less clear. So I think what's particularly interesting about this is that one outlier model. So can I get my mouse over to you? Yeah, so this model is very confident wind speeds are going to increase across Europe. It's a good climate model. All these models have been selected because they have a very good representation of the historical climate. All the other ones we've got within each bar, I think wind speeds are going to go down. So there's no reason for one of these models to be more correct than the others. It's just about what it happens to do. So some of them have stronger climate sensitivities with them. Some of them have more poleward propagation of the jet. But a lot of this, as you can see from those huge bars, is climate variability, which is just the fact the 20-year sample we've got, some of them are windy, some of them are not. So it's really difficult actually to know what we might do about wind power. So this is for Europe, and this is changes on average. The other thing we can look at are those kind of wind and solar drought periods. So this is times where these are days when you're in your bottom 20th percentile for wind and solar power generation. And all the different zones here are kind of just power system operation regions. So we're subnational to do this. And the colors are telling you the number of models where you see an increase in the total number of droughts. So if it's red, what that kind of tells you is we're not getting more droughts. That means it's definitely getting windier and sunnier in that region across all 8 of these models that we're looking at here. Sorry, if it's red. Whereas if it's blue, that means we're getting a lot more wind droughts. And we're very confident about it because all 8 of the models are saying a very similar thing. So although changes in the mean, we're not very certain about it, it's quite interesting for these extreme days. There's not much yellow, particularly for that, for these bottom plots, right, in summer. The summer response to increasing wind droughts, the models all have quite good agreement on. So as to why this is something I'm looking at the moment. I'm quite interested in the circulation responses here and what about these climate models is causing us to have more difficult days. So I've kind of banged on a bit there that wind speed projections are really uncertain. I just thought I'd show you some maps so you can really kind of see what we're dealing with here in terms of the uncertainty in the winds. So these are models from the Primavera project. So these are really state-of-the-art global climate models from the CMIP6 project. Kind of the best of the best, to be honest. These are the high-resolution models. On the left, we've got 5 different models in the rows for seasonal temperature changes. So this is, again, those same periods. This is looking at 2050 versus your history. These all look pretty similar, right? Everywhere is red and everywhere is around the same kind of color of red. We've got quite a lot of confidence in the temperature response. You look over here, all kinds of things are going on. And even within the same model family, so those of you who've used climate models before will kind of recognize MOHC, Met Office Hadley Centre. So those bottom 2 rows are, well, it doesn't matter what it stands for, medium resolution, 1 hourly data. They're 2 ensemble members from the same model. And the response in spring and in winter, it's just totally different between the two ensemble members across the period. So that's just because these huge impact climate variability. It's really hard to deal with this when we're trying to do these kind of projections. You need a huge data sample to feel confident that you've captured this variability and you can maybe extract a signal. And there's also a lot that buzzes around in the media at the moment about this kind of concept of global stilling. So this is a map from a really nice tool, actually, the Interactive IPCC Atlas. So that allows you to just plot all of the data that was used to make the IPCC plots. It's really intuitive, really nice for making things like this. But this is looking at near surface winds. What period are we looking at? This is a high climate scenario, and the difference between near term, so this is 21 to 2040, difference in wind speed. You can really see a profound response over Europe to this kind of stilling phenomena. And I get asked all the time by news outlets like, oh, global stilling, does it mean we shouldn't build wind farms? You know, is the wind going to stop by 2050? And I'm like, well, come on, you know, don't be silly. But it is interesting, right, that we kind of you see in a lot of these projections, although there's variability, when you average enough models together and enough data, you start to see consistent signals, particularly over Europe. And we can also see this kind of in historical data. So there have been some very high impact Nature papers around this topic over the last 10 years. So the first Nature paper came out and it was talking about the downward trend in this data. And it was kind of saying, look, historically, I think this is global average surface wind speed. So across the whole globe, and you can really see it's declining there, right? So the Nature paper came out in 2010 and they talked about why might this be? And they said, well, you know, we're doing a lot of urbanization. Maybe all these buildings that we've put up are actually like slowing the wind down, you know, and they had some reasonably convincing arguments. But then that bit happened from 2010 to 2016. And this is a plot from the second Nature paper that says, actually, that's really slow internal climate variability that we're witnessing there. And if you look at global teleconnections, it relates very strongly to ENSO, to the North Atlantic Oscillation. So we need to be a bit careful when we talk about trends in these variables, especially when the media get involved. So since this, there have been some really interesting science studies. Because I said, so if you use data, regional climate model data, you're often a bit limited in your time periods, but a lot of people run climate models at a bit lower resolution, but for thousands of years. So this is a study by Jan Voland, who's in Germany, and he took this is the I can't remember what climate model it is, but basically he took wind speeds over Europe from a simulation which is something like 4,000 years long. And he's looking there because we're talking about trends, right? We're talking about upward and downward trends. So every time you see a green point on this plot, that means there was a significant upward trend that started from that point in the data set. And every time you see a red point, that was when there was a downward trend that has just finished. So you kind of see the ups and the downs, and you see over 4,000 years, you've got absolutely loads of these, right? And then if you take all of those dots, you can put them on a histogram, and he's handily put the Nature papers in the dashed lines in that plot. So you can really show that these nature-worthy, profound results really do just fit into climate variability, you know, and that's just the kind of stuff we have to deal with. So it's obviously still a problem if you're at the bottom of that range of climate variability, like in 2010. We need to build our systems to be able to cope with that. But also, you could argue maybe we've got some high wind years still to come, right? If we've got lots of rising trends again. So that might time very nicely with 2030 when we're all really struggling with our net zero targets. Maybe we'll be able to burn a bit less coal in the future. So just to finish up in the last 2 minutes, what I'm working on right now. So I mentioned, I've talked to you a lot about Europe today, but I like to do things that aren't in Europe. Kansas here, should go talk to her later. She did a lot of work over Mexico. So we were looking at tropical cyclones and how they might knock wind turbines down. Also, as I said, we do work over India, Africa. We can really do this for anywhere. We just wait for people to ask us interesting questions. The other thing I'm really interested in is compound events. Candace's PhD is thinking about compound cold events. So if it's cold and wet versus cold and dry, it has really different impacts. But we've got this project, UK project, looking at all these different hazards on the screen and what happens if you get pairs of them versus just one on its own. And the impacts are always worse when you've got two, basically. Even worse if you've got three. But we've been asking the energy and the rail sectors about these hazards and asking them, what decisions do you make? What do you want to know? How can we kind of help you model these a bit better from a meteorological perspective? And the thing I'm actually employed on, I'm on a 5-year fellowship at the moment. So I think continuing all the kind of things we talked about, but the main different thing I'm kind of doing at the moment is really thinking about early warning systems. So it's all very well for me to talk about 30-year variability, but really we need to keep the lights on now, right? So it's also thinking about how can we use weather forecasts in the really near term to prepare the system for the coming winter, coming summer, and provide as useful information as possible to people who are making real decisions. So yeah, I'll leave some of my big thoughts on the screen, but yeah, it was really nice to talk to you all, and I'm happy to take any questions. Thank you.
Thank you, Hannah. That was really interesting. I tend to abuse my power and first question for my own interest, and then I'll hand it to the floor. It's probably more related to some of the topics you talk about towards the end of your talk. So I work with resilience, and some of the main impacts that was become really high impact events is when you've got widespread power cuts, and especially for a prolonged period, and especially when it's followed by a cold spell. So, for example, Storm Arwen with widespread disruption followed by a cold spell is kind of worst case scenario.
Yeah.
How much the communications around predicting faults? How much work is there around trying to predict faults ahead of an event? How widespread it is? It seems to be quite a black box as to how much disruption you're expecting ahead of a severe event.
Yeah, no, that's a really good question. So some of my colleagues at Newcastle have just completed a project that's called CS Now. So that's been all about working. So the first thing you've got to do is know how the weather relates to the faults. So I think they've done a lot of work trying to develop metrics and response functions for how do we go from weather to faults in a way that we don't have too many false alarms, and it could potentially be useful. Now they've done that, they're kind of in forecasting mode, and they have these, I think it's called a consequence forecasting framework. So they work with the distribution networks across the UK. And they've done some pilots, I think they have some case study events where they can show retrospectively, you told us there were a lot of things that happened then, we can kind of forecast that. But I don't know how much is going on in real time, to be honest. I think probably the Met Office are doing the most. But academically, it's really hard to find the right people to talk to because, well, for me, it's very scary, the idea of providing a forecast that was really wrong if people made decisions. I think in academia, we like to be really confident that what we're doing has a really good success rate before we can implement it in the wild. But maybe we wait too long, and then by that point, we don't have the connections and it's all a bit complicated. But yeah, I think there's hope. There's projects thinking about it.
Excellent. So we'll open to the floor, and then I'll start in person and I'll move online as well. Gary, you're first. Hand you this.
Thanks, Hannah. Very, very interesting. But just I've got a question about averaging out. When you said you average out through the UK, and I'm talking particularly about the UK.
Yeah.
Just for clarity, it's really two parts of my question. But for clarity, when you're talking about the power that's been fed into the national grid, the network, are you talking about wind farms and solar farms as opposed to people putting solar panels on the roofs? The reason being, obviously, in Scotland, you will barely see a new house without a solar panel system now, or an alternative heat pump, ground source, or other alternative energy. So I'm wondering how that factors in. But the main part of my question was really to do with, again, averaging out. If you're talking about the same circumstance, same low features over the centre of London or over the centre of Wick or Thurso up there, you're going to get a very different model surely coming from that because of the heat island coming out of London. You could have the same millibars, you could have the same circumstances, isobars there, but a very different demand on the network.
Yes.
So can heat islands be taken, or do you take heat islands into consideration?
Yeah, both really good questions. I'll try and remember them both. Yes, so with the wind farms, it's easy because we know where they are. We don't have to buy that information, which is a bit annoying, to be honest. But, you know, we know where they are. With the solar farms, it's really hard to know. There's no reporting required on people who have rooftop solar. So there's some creative things people have done. Open Climate Fix in the UK have basically used OpenStreetMap and used super clever coding things to basically look at which houses have solar panels on them, read the satellite images, put dots in a box, aggregate up. So you can do it. It's a massive effort, though, to do that, and not in the skill set of some of the people who are working with the weather data. So we know where the big solar parks are, and we have information about that, but that bit is very difficult. So in my solar model, we use population as a proxy. So we assume that where there are more people, there is more rooftop solar. So all of the grid boxes, whenever anything is averaged, it's weighted by population. So there's a much higher impact of the south. So particularly around London, Birmingham, Manchester is where we get our big kind of booms of solar in our model, which might not be representative, but it's kind of the best we can do. The urban heat island idea is really interesting. Again, the demand model is weighted by population because we were like, well, the temperatures in the highlands will not, you know, they do not impact really how this energy system operates. But in terms of more local, so we're trying to build a regional demand model at the moment, which I think we'll need to think about the issues that you're talking about, because the way that London responds is very different to how, say, Dundee responds and to demand. So big challenges that you've highlighted there. So we're trying to deal with that.
Thanks. Yeah, really good, really interesting talk. Thanks very much. So my question is about the mix of different energy sources. So presumably it's really important that we don't have all our eggs in one basket, and we don't just have lots of wind power and nothing else. So am I right in thinking, I think I've heard this said, that there's a strong anti-correlation between wind and solar. So I suppose my question is, do we have the right mix, and are people thinking about getting the right mix? And does that help if we do have the right mix?
Yes. So definitely you don't want to put all your eggs in one basket. You can, but you need friends. There's a lot of academic studies on this. So there's basically, if the UK has a few options. The Boris plan was I love this quote because it's so silly. We were going to become the Saudi Arabia of wind power, and we were going to go wind only. And when we had too much, we'd just give it to all our friends. And we would hope that when it was sunny in Spain, they would send it through the channels up to us, which that is, it could work, but we're not well interconnected enough as a continent for that to work. So on a much smaller scale within a country, absolutely right. So in summer, wind is low, but solar is high. And there's a lot of studies where you can find sweet spots, because although wind is super variable on this year-to-year time series, solar is not. There's different challenges with solar, because solar is really hard to forecast. If anyone's a forecaster, where's a cloud? Because a cloud that would take out your local solar is probably smaller than a grid box that it's being modeled in. So that's hard, but year to year wise, it's basically the same every year. You just have this strong seasonal cycle. So in theory, you can get this like optimal point where you can go 100% renewable with just wind, solar, and a good battery. So you're always filling the battery up from one of them, discharging it a little bit, and kind of yeah, it's quite exciting to try and find that sweet spot. I didn't talk too much about solar today, but it's really helpful to remove some of this variability of wind.
Is the UK anywhere near the right balance at the moment?
No, we're really high on the wind end. So the problem we have as well is that you will know it's not that sunny in the UK, particularly in winter, right? So if you it's very easy to Google actually. If you just Google kind of a solar power time series, the amount you get in winter is like less than a fifth of what you get in summer. So we need to have basically on everyone's house, we need solar farms to start to get enough that it was even starting to be enough in winter. But you have to work with what you've got, right? We're in the North Sea. It makes a lot of sense. Like wind power is very cheap now. And it is good power. It's just we need these kind of management tools to work with it, like the batteries or just turning it off, knowing when to turn it off.
Thank you. Are there any questions online? If the Yeah, Roy, you should be able to ask the question directly to Hannah if you wish, or we can read it out ourselves here.
Just wondered if I could put them on the screen, but that might be beyond my skill set.
Yes, I can try to ask the question. I think David's partly covered it.
Hello. It's Zoom.
No problem. We can read the question out. Roy, if we... No problem. We can move to the chat section.
Yeah, no worries. Oh my goodness. It's a big one.
There's Roy's question there.
Your demand model forced by 40 years of reanalysis looks to be very... Oh, thanks, Roy. But in your model future, did the UK population Oh yeah, great question. Every 5 years or so in era 40 without massive. Okay, yeah. So the question is demand model.
Okay, and if you could quickly summarize the question and then answer.
Yeah. So Roy is making a good point. So he's kind of saying like, can't multitask. Sorry. Yeah, so when you have these really long Dunkelflaute events, so Roy's kind of asking, how do we keep the lights on throughout them, I guess, in this modeled world? And without unaffordable storage or vast interconnection, shouldn't everyone in the UK have died? Thanks, Roy. No, it's a good question, actually. So as much as I probably shouldn't say it, as someone who's enthusiastic about getting to net zero, we're never there's always going to be contingency in place, right? I think we're never going to shut down the gas. We'll try really hard never to use it, I think, in a net zero world, but I imagine it always will be there. It's just really not feasible for the government to let everyone die because the wind and solar wasn't around. I think if you look in the stats of that plot I was showing, the longest event you ever see is about 10 days, as you're saying. But if you think about by that point, if we're that renewable dependent, the spatial extent of them is never that far. So we might be having a 10-day event, but France will maybe only be having a 2-day, and Germany's having a 2. So there's power somewhere in Europe for all of that. So we can share power. We also, in theory, have very expensive storage solutions available there. So I think we will progress slowly enough that it will never be that catastrophic. And we'll always have contingency in place. Good question though.
Jeff, we'll try one more time. If you want to try and ask your question directly to Hannah, and then if not, we can summarize it.
Yeah, hello, can you hear me?
We can indeed. Perfect. On you go.
Right. Okay. It's just you've mentioned in passing 2 or 3 times that you've talked about interconnectors, and then you just said something about it's a long way to bring it from Spain. I'm assuming that these interconnectors between countries are a growing art, and there will be more and more of them. I mean, is it something you're aware of?
Yeah, great question, Jeff. So we have quite a lot. So we, as the UK, I think we have about 5 at the moment. So we're connected to Ireland, northern and southern. We're connected to France. We're connected to Norway. That one opened last year. We're connected to Belgium. So we've got just as well. We've got lots. We're in Ireland, and we're the UK. We ask for lots of things. So that's a lot of different places we can get power from, right? Through all those different interconnectors. Each of them are about, test me now, 2 to 4 gigawatts in size, and our average demand is about 40. So they're a small proportion each of what we need. But that's options, and all of those countries as well. So I use France as the example. I think France is connected to all of its borders as well. So there is a network of interconnection. And the power market is a bit crazy. Like, in theory, energy traders can buy and sell power from anywhere to anywhere. So I kind of say offhandedly, we'll just take some solar from Spain, etc. There used to be talks that we were going to build a big cable to Morocco to take Saharan solar, but that thankfully got axed. But we are interconnected enough as a country, and we have more plans coming online as well. I think there's a UK Denmark proposed, and maybe also a UK. Can't remember what the other one is, but there's a lot basically. So although interconnection is very expensive, it's a way we can do it. It's definitely possible. The other thing that's quite cool that is starting to happen, so some countries like Denmark now have energy islands. So this is basically old oil platforms are getting turned into onshore wind and solar farms. So and with big batteries and electrolyzers. So it's just this little hub of places that's like a mini country that can just make loads of energy, and it could just come through the cable. So it's a great use of a platform that is no longer relevant in today's society, if the oil's gone. And an interesting interconnection option. So yeah, lots of things like that going forward.
Yep. Thanks very much.
Thanks, Jeff. Thanks for your question, and thanks, Hannah. So we're reaching the end of our allotted time, so we'll call it a day there. Thanks for answering all the questions. Another thanks to Hannah for talking to us tonight. Thanks for attending. I want to just give you the advertise our next speech. Our next talk is next month on the 16th of February. David Stevenson and Dr. Katrina Eldman from the University of Edinburgh will be talking about the future of hydrogen economy and the atmosphere, notably the benefits and potential problems for climate. Hopefully we'll see some of you then. We will send you the instructions for the time. But until then, thanks very much for attending and engaging, and wish you all a nice weekend.
Thank you.